Right, here is the mark scheme for the 2016 Year 9 exam, and different teachers have pulled together the explanations explaining why they marked it the way they have. Enjoy.
Good morning, Year 9. Let's start with question 1. Alistair likes to spend his holidays at the beach, blah, blah, blah. Choose the correct answer to the following questions, blah. The photograph shows a wave in a bay. The wave is made by a passing boat. Which of these best describes what is transported by the water wave? Now, remember the definition of a wave is something that transfers energy without the transfer of matter. So, remembering our definition of a wave, water is matter. Matter just means stuff, doesn't it? So it's energy only that is getting transported by the water wave. Electromagnetic waves have the same, is it amplitude in a vacuum, frequency in air, speed in a vacuum, wavelength in air? The answer is speed in a vacuum, which is just a little tidbit that you need to memorize. So well done if you remembered that. In the electromagnetic spectrum, microwaves are between which two parts of the spectrum? You may remember the song, radio waves, microwaves, infrared radiation. A is the answer. State the amplitude of this sound wave. Now remember, amplitude is the displacement between here and here, not the top and the bottom. So the answer is 5 centimeters. The sound wave above is, sound waves are always longitudinal waves. It's a good example of a longitudinal wave to remember. Alistair is considering which media sound waves can travel through. He is aware of a vacuum, fluids, and solids as being the 3 media he has read about. Sound waves can travel in fluids and solids, but not in a vacuum. Only electromagnetic waves can travel through a vacuum. So, solid and fluid media. There we go.
Okay, so we're now looking at question 2, which is all to do with the electromagnetic spectrum, specifically the microwave area. Now, it shows us the bands for these, the different bands in this microwave spectrum. So this is just a part of the electromagnetic spectrum. And it says which band in the microwave spectrum has the shortest wavelength. Now, if you notice in the in the table here, it's actually giving you the frequencies. So the shortest wavelength is going to be the one with the longest frequency. So that's this end here. So the answer they're looking for is band D. Now, the question tells us microwaves are used by mobile phones and also for satellite communications. So state a further use for microwaves. So saying things like satellite TV and things like that, that's all really part of satellite communications. The one they're looking for here is cooking, and obviously cooking food in the microwave oven. Now, you need to be careful here. If you just said microwaves, well, microwaves, what do you mean? You're just saying the word from the question. Microwave oven would have got you the mark. Also, another thing you need to be careful of is saying heating things. Now, all electromagnetic waves, when they are absorbed, they will heat things. However, specifically, microwaves are very good at cooking food, anything that has water molecules in it, because they cause the water molecules to resonate and heat up really fast. So it's a special case for microwaves that they're very good at cooking food. And then the last part of this question, it tells us that the microwaves in the E band, so that's this one here, can be absorbed by oxygen, carbon dioxide, and nitrogen. And it asks why those are not suitable for use in satellite communications. Well, clearly the air contains those gases. So it contains oxygen, nitrogen, and carbon dioxide. And hence these they are going to be absorbed by, okay, so they're not going to get up to where we want to get them to because they're going to be absorbed by the nitrogen, oxygen, carbon dioxide in the air. You need to be very clear with what you're saying, that you're recognising the fact that those gases are present in the air, and therefore as the microwaves have to pass through air, they will be absorbed by those gases. And the next part of the question asks us to work out the wavelength of this wave when it has a frequency of 2 gigahertz, and it reminds us that the speed of the wave is 3 times 10 to the 8 meters per second. Only given this very nice hint here that giga means 1,000 million or 1 billion of something. So first things first, we need an equation. The velocity of a wave is given by the frequency times by the wavelength of that wave. If we rearrange this, we will therefore find that the wavelength is the velocity divided by the frequency, which is 3 times 10 to the 8, so you could write out the zeros, so that would be 300 million, and divided by 2 gigahertz, that's 2 times 10 to the 9. Again, could just write out the zeros. And when you do that, you're going to get an answer of 0.15 meters. Now, name the part of the electromagnetic spectrum to which this wave belongs. Well, in the table beforehand, what we saw was that the lowest frequency band of microwaves was around about 8 gigahertz, and this one is, we're being told that this is 2 gigahertz, so that means it's going to be a lower frequency than microwaves. Now, the only part of the electromagnetic spectrum that has a lower frequency than microwaves is the radio waves. That is the lowest frequency, so that must be that part. Okay, so the next part of the question is talking about these floats that are separated by a certain distance, and it wants us to calculate the distance between the floats. Now, it shows us the waves that are passing by, and if we look at this, we know that if the wavelength of the wave is 0.8 meters, well, the wavelength is going to be the distance between two peaks, okay, two adjacent peaks. That's the distance covered by the wave in one time period. And we can count that there are going to be 1, 2, 3, 4, 5, 6, 7 of these gaps in there. So the distance there must be 0.8 meters times by 7 gaps, which gives us an answer of 5.6 meters. Lots of people counting the number of peaks to get 8, which doesn't give you the correct answer. You need to count the number of gaps between the peaks and multiply that by 0.8. And then finally, if the frequency of the wave is 0.4 hertz, how many complete wavelengths pass each float in 20 seconds? Now, lots of people are overcomplicating and thinking they needed to use the wave equation, but we don't know what the speed of the wave is. We could use this to work out the speed of the wave, but all this is asking us to do is to say, notice that, well, 0.4 hertz means that is 0.4 per second. That's what hertz means. So if we want to find how many complete wavelengths there are in 20 seconds, we need to do the 0.4 per second times by 20, which gives us an answer of 8. Okay, so the answer is C, 8.
Right, this is question 3 in the Year 9 paper. So this is about scales, it's about graphs, it's about analysing data. Mina wants to find the weight of her school bag. She has a weighing scale, but it's marked in kilograms instead of in newtons. The weighing scale is not working properly, so with nothing hanging on it, it shows a reading. So you don't need to read it, that's fine. Right, what is the weight of a 0.4 kilogram mass on the surface of the Earth? That's reasonably straightforward. It gives you the newtons at the end, so all you need to be able to write is that the weight is equal to mass times by g, which is equal to 0.4 times by 10, which you found on the front of your paper, and that's equal to 4 newtons. So the places where people went wrong, of course, was that the calculation error sometimes had 0.4 times 10 equals 40 or equals 400, okay, both of which are not entirely true. So just be careful with your calculator on this one. It's always a good idea to include the equation, although in this circumstances on this mark scheme, you did get the marks if you simply had the implication of using the correct equation, which is 0.4 times 10. So straightforward. Right, here you've got some data to analyse. So this is the one where Mina decides to put the tins of beans in a plastic bag and hangs them from the scale and sees what the reading does. So the number of tins that are put in the plastic bag is something that the person has decided to. In this case, Mina decided to put in 1 or 2 or 3 tins of beans. So that's the independent variable. So the question is, what depends on the number of tins? So this is the independent variable, which makes this the dependent variable. Okay, and that answers the question in the first one. So you could have written simply the scale depended on the number of beans, or the scale reading, or the mass measured. Okay, all depended on the number of tins. So that's why we call it a dependent variable. Okay, the next part of the question. Draw on the graph to show how the scale reading varies with the number of tins of the beans, include the origin 0, 0. That we'll do in the next section when there's a graph page, so I'll have a look at that in a moment. Circle the anomalous point, we'll come to that in a moment. The next bit then says, Mina notices that the label in each tin says 0.4 kilograms of beans, deduce what the graph says. So I'll answer this one here. What you need to be able to do is to realise that this is asking you to deduce from the graph. So just to sketch it very quickly, what you end up with is a graph of scale reading, very small, against number of tins down below. And normally I would do this a little bit more neatly, but the argument is that you get some graph points plotted a bit like this, I think. And the idea is that if you draw your line and it goes right back to 0, then clearly when you've got 0 number of tins, what is the scale reading? And it turns out to be 1.5 kilograms. So you have to indicate that you used the graph to work this out. What lots of people realized was that if you go back up a little bit here, you look at the marks and you say that there is for 1 tin. So what lots of people did was they said 1 tin is 1.9 kilograms. So 0 tins is 1.5 kilograms because each tin is 0.4 kilograms. That's absolutely fine because you'll end up getting 2 ticks for that, but you'll miss out on the tick for this bit here to indicate you used the graph. So you must, if it says something like this in the question, you must make sure you answer the question. The next bit of the question asks you to plot the points on the graph. So I'm going to go ahead and do it as quickly as I can to show you what I would look for when I'm plotting a graph for the first time. It says include 0, 0. So if I'm going to include 0, 0, that's fine. That's the origin in the bottom left. So I can call that 0 and that's 0. Now I need to put my axes on here. So the independent variable is the number of tins. So I'm simply going to write the tins down here. Now that does not have a unit, so I ignore that. Now on the left-hand side, I've got scale reading, so I need to write scale reading. But this is in kilograms, so I must include a unit on that side. So if I'm looking for marks on this, I'll get a mark for axes, and I get a mark for units. Okay, so that's my first two marks. Right, then I'm looking to plot the points correctly. So I want to make sure that my x-axis is big enough, so I could go I could say 1, 2, 3, 4, 5, 6 tins of bins. I simply can't make it bigger than that, so I'm going to go with that. So that's 1, 2, 3, 4, 5, 6. Now the next one is I need to make sure that I've got the scale reading organised. Now my top scale reading is 3.9, so I could easily go 1, 2, oh, excuse me, that 2 won't work there. That's gone too far. That's 1, 2 is here, perfect. So it's got 2 large boxes. 3 is here, and 4 is there. That allows me to use the majority of the graph space, which is what you will have to do in the exams. Right, now I need to plot the graph. So my first point is going to be 1.9 for 1 tin, which is up here. Then the next one is going to be 2.3, which is going to be there. Then the next one at 3 beans is going to be 2.8, which is going to be up here. Let's see, that's 2.5, that's 2.8 is there. Then the next one is going to be 3.7, which seems remarkably high, but that's absolutely fine. And then 5 is going to be 3.5, so it should be reasonably quick. And then the last one is 3.9, which I know is up here. Okay, now what's quite nice about that is as soon as I've plotted them correctly and I've used little crosses to indicate what I've got, then immediately I get one for plotting correctly. Okay, then I need a line of best fit. So the easiest way to do a line of best fit is with a ruler. Without a ruler, I'm simply going to draw it as best I can, like this. And of course, the point about drawing a graph is that you can extrapolate as far as possible. Now, if you were to realize this, it's got to be a spring on this, so therefore it's Hooke's law. So if it's Hooke's law, then it's proportional. Okay, the only problem with this is it's starting not at 0, 0. So if I do a line of best fit correctly, then I'm going to mark for my line of best fit. Okay. Now, the last point then is that I get a mark which we talked about in the previous page, which is to identify by ringing it as the anomaly. And that's my 5 marks anomaly. Notice you don't get any marks for putting a title on it because, of course, it's part of the same question. So that's not important for us here. Of course, it is when you're doing practicals in class, but not here. So what were the things that people didn't do as well as they could have done? Lots of students decided that they were going to do lines of best fit that started, here we go, I'll do this in black, started at the origin. So for some reason, we had graphs that were doing this. They were coming up here and then joining that one. Now that's not correct. Still, other people decided that they wanted to make sure that as many points as possible were included. So some students decided they were going to start here and then they were going to join this one, and they were going to go down to that one and across. Now, it's quite clear that this one here doesn't follow the pattern, so you have to ignore it, whereas the other 5 all seem to follow the pattern quite clearly. So when you're drawing graphs, be very careful like that. Now, the next 2 marks will come from the next page, where it says, imagine that the same experiment was done on a different planet, which is smaller than the Earth, say the Moon or Mercury. Well, what would happen there is that the spring would extend less for the same number of tins. So, for example, for 1 tin, I'd expect a smaller, perhaps say only or a 1 scale reading on it. And then equally for 2, it would also extend less and less in proportion. So it might be something like this. So what am I looking for in terms of drawing my graph? Well, I want another straight line. Okay, so for this one, I'll do it in black here. This is the moon. So I'll get a tick for a straight line, which is a lower gradient. And the second one I'll get is it should hit the y-axis at a lower value than 1.5 kilograms on the y-axis. Okay, that's exactly what we need. The final piece of this question is a little bit of questions about what we've done. So the fact that every measurement is larger than it should be by the same amount, in fact it's larger by 1.5 kilograms than it should be for every single reading. What kind of uncertainty is this? What kind of error is this? It's known as a zero error. Sometimes it's known as a systematic error. Either of those two would do. The reason why it's a systematic means that it is the same for every reading. The idea of a zero error, it's a bit like when you had to zero your Newton meters when you're doing Hooke's law. So that's what we need for that. When she puts a school bag on the scale, it reads 5 kilograms. How heavy is Mina's bag really? Right, it depends on what you got as your value for C in the previous question. But every single value is greater by 1.5 kilograms. So 5 kilograms minus 1.5 kilograms equals 3.5 kilograms, which should be the mass of Mina's bag. Because if there was nothing on it, it would be 1.5, but hers says 5, so therefore the difference is 3.5. So it suggests two reasons why it might not be accurate. There are loads and loads of options you can have here, so I'll list them all here, and then you can choose two that you think are the best ones for you. There's a possibility that the scale may not be linear. So what we mean by that is that it may not be stretching as much for each added extra ton of beans. Another example of that is to suggest that the elastic limit has been reached. And that would explain why it's broken in the first place. So therefore you're not going to get sensible readings for that. The next one is that you could also be reading it incorrectly. So parallax error means that you're reading it at an angle and therefore misreading it. So even if you wrote down misreading the scale, that's perfectly acceptable. Because if you misread it and write down the wrong answers, of course, then that can create an error in any calculation you use. You could also say that the needle was not settled, because quite often the needle bounces up and down when you put something on a scale. You could say that the mass of the tin or the bag wasn't taken into account. Okay, so that would then affect the reading, because of course the beans weigh 0.4 kilograms, but what about the tin and the can and the bag? What other options are there? You could, if you were a bit careful with this, you could say that the line of best fit wasn't drawn properly. There's a problem with that, of course, is that you were the one who did the line of best fit. Or it's inaccurately drawn. So where can we end up with that? Well, a non-linear elastic limit has been reached. It's certainly worth a mark. Misreading the scale, having parallax error, or the needle is not there. The mass of the tin or the bag wasn't taken into account. The line of best fit. There are lots of options about how you can get the mark on this one. Final question says, sketch a second line on the graph paper to show what would happen like if it was on a small planet like Mercury or the Moon. You don't need specific values. We've been through that on the graph. So that's the end of that. It was a very long question for 18 marks. However, it was hopefully scaffolded in such a way that you could have accessed most of those, and the majority of students got about 2/3 of the questions right for that, about 12 out of 18.
Right, gents. This question separated the men from the boys and clearly showed who'd done some revision and who had not. So, the first one that pretty much, I would say, 70 to 80% of you got wrong was state where it might be installed and used commercially. Now, most of you went for the vague option of just putting factory or power plant. You've got to be more specific, because there's plenty of factories that don't produce any smoke. Yeah, so it has to be chimney. Oh, that's gauge pen mode. So it has to be chimney. I would also accept alternatives like a funnel or a smoke outlet or something along those lines. The next part of the question, a lot of people lost marks through laziness. So it says that the waste gases gain a negative charge as they go up through the blue grid. In the diagram above, label the positively charged plates. Now, a lot of you just put some sort of vague label to the side, like so. Now, if you read the question, it says label the positively charged plates, plural. So if you only labelled one plate, you didn't get the mark. So you had to clearly label both of the plates. Otherwise, you didn't get that mark. So a surprising number of people missed out on that mark. I would say maybe 40% of you got the mark, which is a bit shocking, really, for something that just says label. Now, part B, a very large number of you begin this opening statement by saying the waste gases gain a negative charge as they go up through the blue grid. Now, because this is actually written 2 lines above, funnily enough, you don't get any marks for that. So 3 points that are key in this. You need to say that the smoke particles gain a negative charge and are either repelled by each other because they have like charges, or by the grid. I did accept by the grid as well. The second mark is for stating that these negatively charged particles would be attracted to the positively charged plates that a lot of you failed to label earlier. The third mark is for saying that you can just collect the waste, let's stick a bit clear at that. So you collect the smoke particles in the trays underneath. And about one person in the entire year said that the waste gases proceed through unaffected. So well done to that one person. You are that 1 in 250 people.
So in question 5, we've got this man Norman who is pulling his luggage along on these wheels, and he's exerting a force of 13 newtons, constant force of 13 newtons for the 110 meters, and then eventually he stops. That's going to be very important later, the fact that he stops. But first of all, it's asking us to work to deal with the work done on the suitcase by the person. So the equation, work done, is the force that is exerted multiplied by the distance moved. So that's the force times by the distance moved. And lots of people correctly saying that that's in the direction of the force. Now you didn't need those last bits to get that mark, but that will help you get it. And then calculate the work done on the suitcase by the person. So we just need to put the numbers into this equation. Work done is force times distance, which gives me 13 newtons times by 110 meters, which gives me an answer of 1,430 joules. So that was generally well done, those 2 parts. Now this last part of the question, not so well done, which is really just learning. write down the principle of conservation of energy. And that is that energy can neither be created nor destroyed. It's very important that you get both. And also this last bit, only transformed or transferred, either word is fine, from one form to another. So the total energy in the universe is always constant, and it's just we've got energy being transferred from one place to another place, one form to another form, but it's never being created out of nothing or destroyed. Okay, and how much energy is transferred to the suitcase during the journey? Well, this is just equal to the work done. So all of that work that was done is going to equal the energy that gets transferred to the suitcase. So that is the 1,430 joules, preferably include the unit if we can. And where is this energy transferred to the suitcase gone, and in what form is it now? Well, remember back earlier I said it was important that we said that the man has stopped. Okay, so it's not going to be kinetic energy because he's stopped. So the wheels don't have kinetic energy and the suitcase doesn't have kinetic energy because he's not moving anywhere. Which makes things a little bit more confusing. Where has this energy gone? Well, while he was moving along, there will have been some friction, some drag, and things that he had to overcome. That's why he needed the force to keep the suitcase moving. And therefore, this energy has all gone, it's been dissipated by that. So it's dissipated as heat and a little bit of sound, but sound is such a small amount of energy that we tend to ignore it, so it's mostly heat. Dissipated as heat due to friction, and most of that is going to be in the wheels, where basically in the bearings of the wheels where they're spinning. Also maybe a little bit to the suitcase. Lots of people are saying that the suitcase is all the energy is going to go to warming up the suitcase because of drag on the suitcase. That would only really be the case if the suitcase was moving extraordinarily fast, much faster than I think Norman was going to be walking along to the airport.
The mass of a flying squirrel is 190 grams. Write down the mass in kilograms. Now for this, you need to remember that 1,000 grams is 1 kilogram. So for 190 grams, I need to divide by 1,000, 0.19 kilograms. By the way, kilo always means 1,000. So for example, a kilometre is 1,000 metres, and I find that an easy way of remembering. Write down the equation which relates the GPE to the mass of the squirrel, the gravitational field strength, and the change in height. So this, you might have remembered, was GPE equals mg delta h. Delta, by the way, this symbol just means change in. By the way, one thing that we weren't strict about, but really we might have been because in the GCSE they are, is that gravitational field strength has a symbol lowercase g. So be careful of that. Uppercase G isn't the same thing. Now we're going to use this equation. Calculate the gravitational potential energy gained by the squirrel during this climb. Just a reminder, the squirrel climbs 17 meters. And if I just scroll up to remind myself, the mass, remember, is 0.19 kilograms. By the way, in this equation, mg delta h, you have to use the mass in kilograms. So watch out for that, because some guys tried to use the mass in grams, and they ended up with a really huge gravitational potential energy. So let's go ahead and put the numbers in our equation. So we've got GPE equals mg delta h. Remember, mass in kilograms, 0.19. G is 10. If you didn't remember that, we gave it to you on the front page of the whole exam, and the change in height is 17 meters. So then when you put that in your calculator, you should get something like 32.3, and the unit is joules, and actually we gave you the unit this time. So 32.3, job done. So now we have the flying squirrel gliding from one tree to another. Add labelled arrows to the diagram to show the directions, not the sizes, of the forces of weight and drag acting on Alexandra's squirrel. Now, would you believe that a third of the year group actually didn't notice this question and left it out? It was sort of snuck in there. You might not have noticed this little question right here, 2 marks. Take heart, basically, if you were one of the people who made this mistake. At least it wasn't your real GCSE, and you'll never make that mistake again. I know that's small comfort right now, but it is a really common mistake to make, and it's just worth thinking about. Double checking at the end of every question that you've got all the marks. You've addressed all of the marks on the right-hand side of the page. So let's go ahead and try and answer the question now. Let's do weight first of all. Weight always acts straight down towards the centre of the earth, no matter where an object is or which direction it's travelling. So let's do that first. And it says labelled arrows, so I'm going to write weight in there. Okay, super. That's supposed to be a straight line. Now, drag. Drag is another word for air resistance, and it's a bit like friction as well. Friction and air resistance both always act in the opposite direction to motion. So since my flying squirrel is gliding from P to Q, the direction of the air resistance has got to be from Q to P. And we start it from inside the object, drag, just like that. Now, if you were tempted to add other arrows, if you were tempted to add lift, for example, lift is something that usually only acts on aeroplane wings and perhaps birds' wings, and they're because of the shape of the wing. This is, by the way, this is slightly beyond your syllabus, but I thought I would explain now. There is a chance that this squirrel would have a special shaped wing and there would be a bit of lift acting on it, but if you notice, the question does not ask for that. The question only asks for the forces of weight and drag. Another thing that I saw some students mention was the force of thrust. There is no force of thrust acting on this squirrel right now. Thrust only acts on objects that have an engine inside them, generally. So thrust only if there's an engine. Which, of course, this squirrel does not have. So there's just some things to think about there. Okay, state the equation linking kinetic energy, mass, and velocity. This was well answered. Some guys did forget the half, though. So it's kinetic energy equals half times mass times velocity squared. Calculate the kinetic energy of the squirrel as it glides. Okay, here we go. We'll just double check what speed it's going at. 13 meters per second. So we have KE equals half mv squared. Again, the mass has to be in kilograms, otherwise you'll have an answer that's far too large. So half times 0.19, and then the velocity, don't forget to square it, which a few boys made that mistake. Very easy mistake to make. I've seen A-level students make that mistake as well. And you should get an answer that's something like 16.055. And it's nice if you round it. You don't have to round it, you'll still get the marks. But why don't we round it to 3 significant figures there? 16.1 joules. Perfect.
The cell converts chemical energy into electrical energy. The lamp converts this energy into light and thermal energy. Now we have a Sankey diagram, and the electrical energy going in is 50 joules, light energy coming out is 36 joules, thermal energy is the rest. So that's going to be 50 minus 36, which equals 14 joules, 14 joules of energy. Okay. Now, calculate the efficiency of the lamp. The efficiency equals useful energy out over total energy in multiplied by 100 to get as a percentage. So in this case, that equals 36 over 50 times by 100, and that will give you 72%. 72%. Okay. Dominic observed the experiment for 10 seconds, calculate the power of the light bulb if in this time 50 joules of energy is supplied to light. So the power equals the energy change divided by the time taken, which equals 50 over 10, which equals 5. And the unit is the watt, so it's going to be 5 watts. Okay.
Right, this question about steam, water and ice. First, what you had to do for the 4 marks here was try and draw the 3. I think it could have actually been given 6 marks, so I had to interpret how these marks would have been given. So I very simply went for the following. I gave 1 mark for ice, 2 for the water, and 1 for the steam, thinking that the water might be the hardest one to annotate. So let me say draw what I think I was looking for. I was looking for, first of all, something very regular and also with structure. So something that looked not too dissimilar to that. I didn't mind if it didn't reach right to the edges, because being a solid, it can hold its own structure. So regular and so it needs to be regular and have a shape to it. That's what I was looking for. Water, of course, has to fill the container and the molecules slide over each other. So I was looking for something which didn't entirely fill, and it was irregular. So it was, and did not fill. I didn't want it right up to the top. For instance, I wanted you to show me that it has a, gravity holds it down and it has a shape, the same shape as the container. And finally, with steam, of course, you're well aware that steam is much more spread out and moving fast. If any of you put a little movement picture in, that was wonderful. But I definitely wanted it all apart, so it wanted to be spread out and fewer particles. In all honesty, most of you got this all okay. That was fairly straightforward. It was this one. The irregularity wasn't there, and also you often filled the entire container. Good, right. Next bit. How do the particles move? I think that is the key. If any of you got this wrong, it's because you didn't comment on movement, you commented on structure. So with solids, they vibrate about a point. Of course, they do not move, unlike a liquid, which they can move. They can move over each other. A gas, of course, it will move randomly and fill all the space in the container. I often like to reference this one, the idea of filling all the space in the container, because otherwise you're defining a liquid. Remember, if the explanation could explain something else, you're not being specific enough. So it was 1 mark for each of those. The next one talked about Titan and its moons on Saturn's surface is at an average temperature of minus 79 degrees Celsius. So here is the important point here, degrees Celsius, and you want to put that into Kelvin. So what did we require? What did it require in order for you to do that? Okay, so in order to convert Kelvin degrees into Kelvin, you need to understand first of all, of course, that your 0 Kelvin is minus 273 degrees Celsius. Some of you excellently put down 0.17 and did decimal places there. Great. But now you're looking for minus 197. So you're looking for something minus 197 degrees Celsius. What is that in Kelvin? Well, this is just, of course, the difference here. The difference between these two will be the increase from 0. So I was looking for something like minus 197 minus 273. It's quite important there to make sure you've got the two minuses present. Gives you 94 kelvins. This sits at 94 Kelvin. Some of you wrote down minus 94, others wrote down 94 degrees C, etc., etc. Make sure, look for precision here. Kelvin, not even degrees Kelvin. Kelvin, no minus there. The workings are very robust if you make sure you get these right. Good. What's the name given to the lowest temperature in the Kelvin scale? 0 Kelvin was acceptable, I thought, or absolute 0. Maybe I was a bit generous with 0 Kelvin. Describe how the particles, if they move at this lowest temperature. Of course, they don't move. But even better, some of you mentioned that at 0 Kelvin, the energy, the kinetic energy, equals 0. So the velocity will equal 0, which was brilliant. However, this is all I needed, that bit. Superb. That's it. Well done for that question.
Right, question 9 was a bit of a tricky one. A lot of people came unstuck here. The first question was relatively simple, although a lot of people only got 1 mark because they got a bit distracted by the fact that pretty much everyone said that shiny surfaces are good reflectors. So it will reflect the energy back into the submarine. So reflect the radiation back into the interior. A few people did mention that they were bad absorbers. That would have got you the 2nd mark. So they're not very good at absorbing energy from inside the submarine. But very rare were the people that said that they were bad emitters. And I think this is actually a more important point than the poor absorption, which is kind of related to the reflection. Because they're bad emitters, even if they absorb energy from the interior of the submarine, they're very poor at emitting that energy to the outside of the submarine. So they retain the thermal energy that they absorb. Better. Okay, the next stage here, explain how the vacuum reduces the thermal energy. So there were 2 parts to this. So you can have no conduction or convection. Whoops. For 1 mark, because there are no particles in a vacuum. Had some very strange answers to this where people didn't really seem to understand what a vacuum was. or in fact what heat was. There's all sorts of strange talk of heat particles. And when you get to year 12, yes, you might understand that there are some things called photons that you might describe as heat particles. But for IGCSE, let's leave the heat particles into science fiction. So, NASA suggested using a cheaper foam insulation called aerogel, which is cheaper than using a vacuum. But it suggests why this would be less effective. Now, a lot of people just said it would be less effective. Now, you're not going to get a mark for that because it's in the question right there. Yeah, you need to say why it would be less effective. Okay, and the reason it would be less effective is because it contains some particles, so it can still conduct, or you could have put both points if you wanted to, but hardly anyone did. The air pockets will still allow some convection. So whereas the vacuum prevents both conduction and convection, a foam insulation like aerogel will only essentially limit it or reduce the amount of convection. So moving on to the next stage. Now this question was quite difficult to mark. A lot of people just wrote down a sort of memorized answer for why you get land and sea breezes. Now this isn't quite the same question. It's a very similar question, but it's not the same. And so if you start writing about land and sea and things, it gets a bit confusing because you're going off from what the question is actually about. So, any two of the air is heated by the ground. A lot of people got confused and said the air is heated by the sun. But if the air is heated by the sun and it's all essentially in sunlight equally, why do some bits of the air get heated more than others? It doesn't make sense. So the air is heated by the ground, chaps. The particles of air will gain kinetic energy. They move faster. And so consequently, the spaces between particles increases. Now there are a few people where the language you were using was a little bit more vague, and it could be construed that you were implying that the particles themselves were expanding, which of course does not happen. So this means the air is less dense, and so rises. Now, you only get a maximum of 2 for any of those points. Okay? So any 2 of those points. Hang on a second. Right, the third essential point. Now, if you're going to get 3 marks in this question, you had to have put this point down. Okay? You had to say that air from the surroundings was drawn in to take the place of the risen air, essentially. Now, you could say sucked in, or was moved in, or went from a high pressure to a low pressure to take the place. But the key thing is this movement of air that causes the wind. And if you look at the question, that's the key point to this question. What causes the movement of air that we call wind? So if you don't have this final point, I'm afraid you can't get the 3rd mark, no matter how many of the previous points you have. Now, this last one, it's just 2 marks, and all it's asking you to do is apply what you know, essentially about a cold area and a hot area, just like in the land and sea breezes, to explain the global wind pattern on Titan. So in the south, it's hotter, and this causes the gas to rise. So air from the north, at low altitudes is drawn in to replace it. The hot air is pushed by air rising behind it, and travels at high altitude. To the north. This was a very difficult question, and a lot of people scored sort of mid-range marks on it, so we're talking about 6-7 marks. If you were in the 10 and 11 mark, then very well done, because you've done extremely well. So, well done.
Okay, this part of the question deals with statics, and it's looking about why this girl's hair is sticking up at the end. So it says Amelia has been jumping up and down on the trampoline. She's gained a negative electrical charge. Fill in the blanks using the words below. So let's just run through those together. Move that up slightly so you can see it all. So it says that as Amelia's coat rubs against the rubber floor of the trampoline, something will move from the rubber of the trampoline, and stick to her. Now, in all cases here, you need to bear in mind that it is electrons that move and not protons. So in any case, if they've ever said something moves, then always reference the electron, because that's what's moving, not protons, electrons. People often get that wrong. The rubber floor of the trampoline becomes, now which way is it? If electrons have been removed from the trampoline onto Amelia, then that must mean that this has an absence of electrons, hence this is positive. So if you're feeling a little bit nervous, you can take those out. And then, because it has lost electrons, I've just explained that. Lost the electrons. Her hair stands on end because the individual strands. Well, interestingly here, why is it that the hair stands on end? Well, you've got, if it's becoming charged, because she's gaining electrons, then each of these is gaining an electrical charge as well. There are lots of them, and therefore they all repel from one another, because like charges repel. Therefore, the correct term here would be, individual stands something each other, repel each other as a negative charge, and same charges repel. Superb. Okay. Reference there, always about electrons moving. As she touches the metal pole of the trampoline frame, and her hair that was standing up now returns to normal. There are 4 explanations. Draw a ring around the correct one. Let's just take a quick look at what's good and what's bad here. Protons from the ground. Right, I told you straight away that protons do not move. Protons do not move. So therefore, we have one of B or C. So electrons flowing from the ground to her neutralized, or electrons flow from her to the ground. In order for it to be neutralized, we have to get the removal of excess. And because she has an excess of electrons, therefore, this is it. It's D. Okay, let's move on and look at the next bit. We are in this one looking at Dom sets up a circuit. He wants to investigate the characteristics of the electrical charge. Wonderful. Jenny says it's good that Dom has put the ammeter in the position shown. If he'd connected it between the lamp and the switch, the current would have been used up by the lamp. and a lot less to measure. Is Jenny right? Explain your decisions. Okay, well, what we ought to think about here, first of all, is a little bit of explanation of what goes on. What happens is charge comes out of that battery, and the charge is carrying with it energy. And as it goes around these lumps of charge, the energy gets used up in the component, and the remainder of the charge goes back to the battery once closed to get recharged, and then the process starts all over again. Now, the reference here is the ammeter is put in the position shown, so we're looking at the ammeter, and the current. So the other key term is the current and the ammeter. Now, the current represents the flow of charge. Or in other words, how many bits of charge are moving. It does not reference, this is not a reference to energy. Okay, these keep coming out. They move through the ammeter, they don't get used up, they just go straight through the ammeter, they come down, they go straight through there, they go back, they're like train cars running around in a circle. The energy gets used up certainly as it goes through there, but it's looking for the current. There's still the same amount flowing on this side as there is on this side, and this side. That is a critical part of understanding electrical currents. So very simply now, to answer the question, we were looking for 2 marks. No, that's 1 mark. And because you can mention in a series circuit, which this is above, the current stays the same in all parts of the circuit. So a reference to why it does not change. Good, okay, I think I've pretty much answered the next one as well. Define what is meant by electrical current. Well, what we're looking for is we're looking for rate of flow of charge. So this is the important point. Charge, those bits flowing around. Rate implies how fast it's moving around. Or, indeed, you could say the number of coulombs per second, which is an even better description of what it is. In other words, the number of charge is coulombs, and the rate is how fast, so how many is moving in a given time per second. So either, put a big or that one. That would get you marks. This, I think, is just something you ought to learn. That definition you'll need and continually need from here through to A level if you want to take it that far. So you might as well just learn it. Fantastic. Okay, moving on. Here we are. We're moving on to the last bit now. It says, oops, sorry. The lamp is running for 20 minutes. Oh, apologies again. With a total of passes through. Good. Right. Let's just make sure. We've been given 20 minutes. We've given a number of coulombs, and we're looking for the current, and we've got 4 marks in order to do it with. So how do we do this? Right. Equation first. Q equals I times T. I'm sure you all remembered that equation. But we're looking for the current, so therefore the current, which is I, a little rearrangement, Q over T. In other words, I've just moved the T down below the brackets there. Good, what have I got then? Let's say I've got 720. There is my coulombs. Time, of course, is 20, but, exclamation here, that's given in minutes, and ideally we want it in seconds. So 20 times 60 gives me 1,000 200 seconds. So this divided by 1200 gives me 0.8, sorry, 0.6 seconds. Okay, where do the marks come in? 1, 2, substitution 3, sorry, will probably be given answer unit. So 1, 2, 3, 4. Easy pickings because you would have known that anyway. Circuits in series. Dom decides to add another identical light bulb in the circuit. He first places a new bulb in series and measures the current. He then connects in parallel. And you want to reference what will happen considering the first one. So how would the ammeter reading compare in these two cases? Explain your reasoning. Well, what do we have? I'm going to draw them just so we know what's happening here. In other words, we had in the first instance a nice light bulb in the circuit. Couldn't find it there, but I'm guessing it looks like this ammeter. So this is our reference. Now, in the series case, we are asking what's going to happen if we stick another one in. What's going to happen to the ammeter? And what you should know is the coulombs coming out of there, they're taking the energy around, but only using up half of it through there and then the remainder through the next one. So what happens is it slows. And if it's slowing, that implies the ammeter is decreasing. And because I've got two lots of that, the ammeter will go down to half the value. So it halves, assuming these are identical. Okay, so think about that. Because there are more obstructions here, double the number of obstructions of light bulbs, the ammeter doesn't obstruct, double the number of bulbs, it won't go round as fast. It goes round slower. Because these are identical, it goes around half as slow. Okay. And the next one then is with a parallel circuit. So let me draw the parallel circuit. One there. And a little bit of you have to make a jump to understand that here they're putting in parallel and you're looking at how much is coming out of the battery. So therefore the setup would be like this. Now this coulomb that comes around chooses either that way or that way. If it chooses this way, all it's got to do is jump through one of them. So therefore it can go through at the same speed it did with that one. So that ammeter reading will be the same as if there were an ammeter right there, because this coulomb's choosing. The one that goes down here has also made a choice, so the next one might make a choice to go through there and go through with the same speed that it did here. So these now are identical and of that value. So therefore, in order to supply enough going out, there must be twice the same amount going out and twice that returning. So therefore it's double. Good. I hope that all makes sense. And I hope that you aced it. And if you didn't ace it, then you have got this opportunity to go through and make sure you get all the right answers.